Good evening and welcome everyone to the sixth problem solving session of the course Computational Continuum Mechanics. I'm Naresh. I'm a research scholar in the Department of Civil Engineering at the Indian Institute of Science, Bangalore. So today, the plan for today is to have three main sections. The first part will be clearing some doubts that was raised by a student. Then we'll look at some interesting theorems, transport properties. We'll derive them so that you get practiced in the tensorial notation. Then finally, we'll solve a problem similar to the one given in your assignment that is due on Wednesday. So that will help you with computing principal stresses in other areas. So let's get started. So this problem was brought up by Sarvesh. This was also taught in the regular lecture by Sir. Let me. So the problem says there's a quadrilateral finite element of size 2 cross 2 and centered at the origin. This one deforms as shown in the figure. The natural coordinates xi1 and xi2 can be placed at the origin O. For a material point which is at the origin, find the deformation gradient tensor, the right Cauchy Green deformation tensor, the green Lagrange straight tensor, and other stretches. So let us solve the problem as follows. Yeah. Let me. So this borrows some concepts from the finite element method. So we have a quadrilateral finite element of this size, and it is centered. So let's sketch it. So you have a quadrilateral element. It's of size 2. So this is the point minus 1, 1. This is the point 1, comma 1. This is the point 1, comma minus 1. And this is the point minus 1, comma 1. And how do they name it? They call this node 1, 2, 3, 4. So let us put nodes on these. This is a node. This is a node. This is a node. And this is a node. So this is node 1. This is node 2. This is node 3. And this is node 4. And this deforms to some other quadrilateral. It is like this. And say this is node 1, node 2, node 3, and node 4. What else is given? It deforms as shown in the figure. The natural coordinates can be placed at the origin. Yeah, so the natural coordinates can be placed at the origin for x equal to 0, 0. So uh, let me use a different color. So this is a chunk of material that is undergoing deformation, and you're considering a particular point at 0, 0. So this is a material point. Let us call this material point P. So this material point, as this square deforms, will be somewhere here. It may no longer be at the center, but it will go to another small p, let us say. So initially, the coordinates of the point capital P are 0, 0. And as it deforms, it goes to some other point. We'll see what that point is. For x equal to 0, 0, this is the thing. Then some more details are given. What it is? This one. Oh, sorry. Could you tell me the coordinates of these points x1, y1, x2, y2, the nodes 1, 2, 3, 4? Did he write it down here or? Yeah, let me check. So in order to be able to write this deformation, we need to know the coordinates of the points, material points x1, x2, x3, and x4. Or rather, let me put a 1. circle here. So this is not the component x1. This is the coordinates of the point nodes 1, 2, 3, and 4. Let us write down what they are. Okay, I think the only way to do it is get to the lecture directly. Yeah, so these points are given. This is the initial, yeah, this is the full diagram. So initial points are fine that we can get just from this information. It is of size 2 cross 2 and it is centered at x equal to 0, y equal to 0. And after deformation, then 4 nodes get to these points defined by small x1 equal to 4 comma 2, 8 comma 4. Let me just write it down. So initially we know their coordinates. So node 1 is at -1 comma -1. Node 2 is at 1 comma -1. Node 3 is at 1 comma 1. And node 4 is at -1 comma 1. And here, what are the nodes? So 1 goes to 4 comma 2. So 1 goes to 4 comma 2. 2 goes to 8 comma 4. 3 goes to 6 comma 8. And the last point goes to 4 comma 6. So after deformation, the coordinates of these points are small x1, which is 4 comma 2, small x2, it is 8 comma 4, x3 is 6 comma 8, and x4 is 4 comma 6. Now we are given the displacements or the deformation at 4 points, right? So you know that phi is a mapping which takes the initial material point coordinate and the time at which and the current time and returns the final position of the point referenced by this material position vector capital X. So here we have 4 such points, and for these 4 points we know the mapping, right? So this defines the mapping for these 4 points. So x1 goes to this point, x2 goes to this point, x3 goes to this point, x4 goes to this point. Time is not really important. You just put some time is equal to t naught. Here time is t naught greater than 0. Here time t is equal to 0. So initially we are referencing 4 nodes, and the 4 nodes are at these points. So we are taking just a unit by unit square, and you're putting the edges of these 4 unit squares. And after deformation, you're looking at the same 4 nodes where they are going. They are going to these points. Therefore, this basically defines a discrete mapping, discrete deformation mapping. Now let us see how this the interpolation works, right? So we are given for 4 points, and we are given a point P which is inside the square bounded by 1, 2, 3, 4. So analytically, we don't know that we don't really know where this point goes. So what people do is we use the finite element mapping. So this is where approximation comes in. Finite element shape functions. So you may be aware of interpolation in one dimension. You have a point x1, you have a point x2, and you know the value of a function f of x1, and you know the value at some other point f of x2. Suppose you are given a point x somewhere in between the two, x is now equal to x2, and you're asked to estimate what is f of x. You're given only the values f of x1 is y1 and f of x2 is y2. So in between, there are various ways to do it. One of the simplest is you do a linear interpolation, right? With 2 points, you can at most fit a straight line through the two. So you fit a straight line between the 2 points, and you call this as f of x or f tilde of x, where f tilde is a linear interpolant. Right? What is f tilde of x? We use the Lagrange interpolation functions. So in this case, to linearly interpolate, what do? We pass a straight line. So you can write this as f of x is equal to, or put a tilde, f tilde of x is equal to f of x1 plus, so this one plus the slope times the difference, right? What is the slope? Slope is f of x2 minus f of x1 divided by x2 minus x1 multiplied by how much is the coordinate? X minus x1. If you do some rearrangement, you can get it to this form. So just do some rearrangement. So you will get, let us have f of x1 multiplied by some function and f of x2 multiplied by some function. So collect all the terms that have f of x1. So you have 1 plus x minus x1 by x2 minus x1. So this one, there is a minus f of x1. So that I'll put a minus sign. And what is this, the thing with f of x2? It is x minus x1 by x2 minus x1. Now simplify the first term. You get f of x. The linear interpolation, a linear interpolant is defined as f of x1 times, do the simplification. So you get x2 minus x1 minus x plus x1. So I get f of x multiplied by x2 minus x by x2 minus x1 plus f of x2 multiplied by x minus x1 by x2 minus x1. So these do depend only on the endpoints and not on the function value at the endpoints themselves. So these are called shape functions. So you don't really, it doesn't really matter which function you're trying to fit. You only need the endpoints. Given the endpoints, you can always write down the function value at any intermediate point as a linear combination of the function values at its endpoints. And what is the linear combination? It has got some coefficients, and those coefficients depend only on the distance of this point from the endpoints. So these are called shape functions. So corresponding to the point 1, first point, you call it an n1. Corresponding to the second point, you call it n2 shape functions. So in general, given n number of points, so in 2D, in 1D, you are given 2 points. And if you want to get the value of a function at somewhere in between the 2 points, given the values of the function at the ends, you write this as f of x at the midpoint is nothing but f of x1 n of x n1 of x plus f of x2 n2 of x. These n1 and n2 have certain special properties that the function that is multiplied with f of x1 will be 0 at x2 and it is 1 at x1. So if you put x equal to x2, this function n1 of x2 will be 0 and n1 of x1 will be 1. Similarly, n1 of n2 of x2 will be 1 and n2 of x1 will be 0. So this you can actually check. N1 of x2 is 0. Just put x equal to x2 here, it will vanish. If you put x equal to x2 here, this will become 1. N2 of x2 will be 1. So these are called, this is the Kronecker delta property. So every shape function is 0 at the nodes, at the other nodes, and it takes a value of 1 at its corresponding node. Analogous to this in 2D, we have something else. So in 2D, we are having this, right? We right now have this. We have 4 points, and you want to find out the function value at somewhere in between. Say you have a point x comma y, capital X comma capital Y. And these have x1 comma y1, x2 comma y2, and so on. How do we interpolate here? So let us use the 1D interpolation functions, right? So this vertical line is nothing but, what is this vertical line? This vertical line is x equal to x1 line. And on this vertical line, it is x equal to x2. On this line, it is y equal to y1 line, and this line is y equal to y2 line. So on the line x equal to x2, the shape functions of this node and this node should be 0, because the shape functions of a given node are 1 at that node and 0 in all other nodes. Now, if you want to write down the shape functions here, let us start with the basic n1 in 1D, right? Let us start with this. So for simplicity, let us take the square from -1 to 1 to 1 to 1. Let us take the unit square. So node 1 is -1 comma -1. Node 2 is 1 comma -1. Node 3 is 1 comma 1. And node 4 is -1 comma 1. So on node 1, we want a function that is 1 at this point and 0 everywhere else. So let me define that function. Let us look at that function as 1 minus. So here it is -1 -1. So let me start with my 1 minus x, 1 minus y. Right? If you see, if you substitute x equal to 1, if along this line x equal to 1, right? Along this line x is equal to 1. And along this line y equal to 1. So if either x becomes 1 or y becomes 1, this function will vanish, which means on these 3 nodes this function will vanish. And when x equal to -1 and y equal to -1, what value this takes? It is 1 minus -1, which is 2, and 1 minus -1, which is 2. So this takes a value of 4. But to get shape function, we just divide it so that it takes a value of 1. So this is n1 of x comma y. Second node is this, right? Second node is this. So here x is +1 and y is -1. So whenever x is not +1, this has to vanish, and whenever y is not -1, this has to vanish. So put 1 plus x, 1 minus y divided by 4. This is n2 of x comma y. You can check. Again, substitute x equal to 1, y equal to 1, this will vanish. X equal to 1, y equal to -1, this will be this point. X equal to -1, y equal to 1, this will vanish. And x equal to -1, y equal to -1, this function will vanish. Similarly, for the third node, x equal to what? X equal to +1, y is equal to +1. Can you guess what should be the form of shape function? As usual, it should be divided by 4. So this is n3 of x comma y. Can you guess what should come here? This has to be 1 at 1 comma 1 and 0 everywhere else. Yeah, you can give it a try. So this should be 1 plus x, 1 plus y, right? So when x is 1, you get a 2 here. When y is 1, you get a 2 here. In all other cases, either x or y is -1, so it is 0. And for the fourth nodes, it is simple. It is x is -1, y is 1. So you get 1 minus x, 1 plus y by 4. This is n4 of x comma y. Now we got these 4 points, right? So similar to 1D. In 1D, what is the question we asked? We are given the function value at 4 points. And you have a point somewhere which is in between the, we have the function value at 2 points. And so you have a point in between the 2 points. How do you estimate the value? You interpolate. Similarly, you interpolate in 2D. So here we interpolate in 2D. right? Interpolate in 2D. And how do we interpolate? We are given the function value at 4 points, and you have the you're asked to find a point P lying inside the 4 points. How do you do it? Just as in the case of 1D, let us call, in this case, the function is a function of two variables. So let us, what is the function actually you're looking at? It's a deformation function, phi of x comma y. What it is? It is phi of x1 comma y1 times n1 of x comma y plus phi of x2 comma y2 times n2 of x comma y plus phi of x3 comma y3 n3 of x comma y plus phi of x4 comma y4 n4 of x comma y. Do we know these? What is phi of x1 comma y1? What is phi of x1 comma y1? It is the final position of the point which was initially at x1 comma y1, right? That is the deformation function. So phi of a point x, which is a vector, is nothing but small x, which is the final position of a material point which was initially at x, right? So phi of x1 comma y1 is what? It is nothing but small x1 comma y1. Therefore, the deformation function is given as small x1 comma y1 multiplied with n1 of x comma y plus small x2 comma y2 multiplied with n2 of x comma y plus small x3 comma y3 multiplied with n3 of x comma y plus small x4 comma y4 multiplied with n4 of x comma y. n1, n2, n3, n4 we already know. This is a scalar function of two variables. Scalar function of two variables. On the other hand, the displacement field is a vector function of two variables. The deformation function is a vector function of two variables. This is a point, right? It's just a point. It's not a function. It is a point. It's a vector point. It's a vector point. It's just a point, right? It has two coordinates and it doesn't have any x or y dependence. So let us write down the deformation function. Phi of x comma y is nothing but, what is the first point? It is, I don't remember. I have to go back. 42846846. So 4 comma 2 n1 of x plus 8 comma 4 n2 of x comma y plus 6 comma 8 n3 of x comma y plus, what is the last one? 4 comma 6. n4 of x comma y. Save the file. So be careful. So this is all the functional dependencies here. n1, n2, n3, n4 are scalar functions, and these are all vectors. These are constant vectors These are scalar functions. Can we write it in a more elegant form? Yes. You can write this as, you can arrange these constant vectors in a matrix form. So put it as 4, 2, 8, 4, 6, 8, 4, 6. And arrange these scalar functions in a column vector. n1 of x comma y, n2 of x comma y, n3 of x comma y, n4 of x comma y. So if you want to cross check, just do expand out this matrix vector multiplication. What is the first number? What is the first? So this result will be 2 cross 1, right? So this is 2 cross 4 multiplying 4 cross 1. So result should be 2 cross 1. What is the first result? If you see here, it is 4 times n1 plus 8 times n2 plus 6 times n3 plus 4 times n4. Here, if you do this, you'll get the same thing. 4 times n1 plus 8 times n2 plus 6 times n3 plus 4 times n4. So this is phi, right? This is the deformation function. What are they asking in the question? We are asked to find out the deformation gradient. We want to know the deformation gradient. So phi of x comma y we want to find grad phi of x comma y. How do you arrange it in component sets? It is partial phi1 x1 phi1 y1 phi2 x1 phi2 y2. Right? Dou phi1 by dou x1, dou phi1 by dou y1, dou phi2 by dou x1, dou phi2 by dou y2. So this is how you in some basis, in a specified basis, the components of the gradient vector gradient tensor are these. You take the first component of the deformation, differentiate with respect to x1. So take the second component of deformation, differentiate with respect to take the first component of the deformation, differentiate with respect to x1 and y1. Take the second component of deformation, differentiate with respect to x1 and y1. Here we have, this is in the product, the first row will be the first component and the second row will be the second component. How do you write down the two other differentiations? So you want to differentiate with respect to x1, x first, then y, right? So, okay, let me see. Am I using, yeah, xy is right. It's right. There's no x1 and y1, there's just xy. In two variables is at x and y. Now again, if you see the function dependence is only in this one, right? You don't have a dependence of other things on. So this let's just do this. So what we want dou phi by dou x1, dou x and dou phi by dou y. So this is a 2 cross 1 vector. This is a 2 cross 1 vector. So the resultant is a 2 cross 2 deformation gradient tensor. Let us see what this is. So first component is nothing but dou phi by dou x, and it is nothing but 4 2 8 4 6 8 4 6 dou by dou x of this multiplying n1 of xy, n2 of xy, n3 of xy, and n4 of xy. So it's a matrix vector product. This matrix is independent of x and y. So this derivative will act only on the second vector. So it is nothing but 4 8 6 4 2 4 8 6. Let me put dou n1 by dou x1, dou n2. Sorry, we make it bigger. Dou n1 by dou x, dou n2 by dou x, dou n3 by dou x, and dou n4 by dou x. Similarly, what about the second column? Second column will be dou phi by dou y. And that will be in similar fashion. We get 4, 8, 6, 4, 2, 4, 8, 6. Dou n1 by dou y, dou n2 by dou y, dou n3 by dou y, and dou n4 by dou y. Now you just want to collect these two in one matrix, right? Dou phi by dou x, dou phi by dou y. This will be your grad phi tensor. In order to collect this is the same. Whatever is pre-multiplying this, in both cases, it is the same matrix, right? So you can take that matrix commonly out. So this will be 4, 8, 6, 4, 2, 4, 2, 4, 8, 6. And here you have a matrix. So this is a 2 cross 4 matrix, and here you will get a 4 cross 2 matrix. What is the 4 cross 2 matrix? It is dou n1 by dou x, dou n2 by dou x, dou n3 by dou x, and dou n4 by dou x. What is the second column? All the shape functions differentiated with respect to y. Dou n1 by dou y, dou n2 by dou y, dou n3 by dou y, and dou n4 by dou y. So we got the deformation gradient, which is f. Only thing that is left to do is we have to actually compute these derivatives. Let's do that. It's very simple. And if you go back to the question, they're asking us to find the derivatives at the origin. Okay, so let us do that. What is n1? N1 is, we found n1 is 1 minus x, 1 minus y by 4. What is dou n1 by dou x? It is minus 1 by 4 to 1 minus y. What is dou n2 by dou x? Sorry, dou n1 by dou y. Dou n1 by dou y is, again there's a minus sign here. It is minus 1 minus x by 4. So when you substitute x equal to 0, y equal to 0, this derivative at the point capital P is minus 1 by 4. And the derivative at the point capital P, at the origin, it is minus 1 by 4. Similarly, what is n2? N2 is, what is n2? 1 plus x, 1 minus y by 4. So the derivative of n2 at the point P is what? So it's positive. So you get a plus 1 by 4. And the derivative of n2 with respect to y at the point P is what? Y has a minus sign, so that minus will get multiplied, you get minus 1 by 4. And n3 is 1 plus x, 1 plus y by 4. So the derivative of, partial derivative of n3 with respect to x is what? 1 by 4. And the partial derivative of n3 with respect to y is 1 by 4. n4 is 1 minus x, 1 plus y by 4. So the partial derivative of n4 with respect to x is what? So x, you have a minus sign, so that minus will get multiplied. You get a minus 1 by 4. And partial derivative of n4 with respect to y is 1 by 4. Okay, so this is 1 by 4. Now collect all these in a matrix form. You get minus 1 by 4, minus 1 by 4. Let me just write it down. So if you collect all these derivatives in a matrix form, you get minus 1 by 4, minus 1 by 4. The second point, x is positive, so 1 by 4, minus 1 by 4. Third point, both are positive. And last point, x is negative. What was the matrix before that? 4, 8, 6. So this is the matrix. This is a derivative of the shape function matrix. This is the constant matrix. This did not change from the beginning. This 4, 8, 6, 4, 4, 6, 4, 2, 4, 2, 4, 4, 6, right? 2, 4, 8, 6, sorry. 2, 4, 8, 6. What is this? Directly we have the gradient of this tensor, gradient of this deformation. This is the deformation gradient. Also call it f. So multiply, we'll see what do we get. We'll get minus 4 plus 8 plus 6 minus 4 by 4. And here you get minus 4 minus 8 plus 6 plus 4 by 4. Here you get minus 2 plus 4 plus 8 minus 6 by 4. And the last one is minus 2 minus 4 plus 8 plus 6 by 4. So let's take the 1 by 4 out. Take the 1 by 4 out. So minus 4 plus 8 is 4. 4 minus 4, so 6. Here you have a minus 4, minus 8, minus 12, minus 12 plus 10. You have a minus 12 plus 10, so it is minus 2. Here we have a 4 plus 8 is 12. 12 minus 6 is 6. 6 minus 2 is 4. And here we have minus 2 minus 4 plus 6 gets cancelled. So 8 by 4. Just we have an 8. Here we have an 8. So minus 2 minus 4, 6, 8. Here minus 4. So just substitute this. You get a 1.5 minus 0.5, 1 and 2. So this is the deformation gradient at the origin, assuming linear interpolation of the deformation field. Now let us see if this answer is correct. I don't remember if this is what they got. You can see. Let us just check the final answer. Yeah. 1.5 minus 0.5 minus 0.5, 1 and 2. So that's the answer. Is that okay? This was the doubt that you had. Is that okay? Yes. Sarvesh, is that okay? Okay. I'm not able to hear you. Your mic remains muted, so I'll just assume. I think it's okay. If you have any problems, you can write to me. You can also put it in the forum. Now let us proceed and solve some more problems in kinematics and balance laws. Okay, so it started with balance laws. So I'm not going to redo the theory that has already been done in the coursework. So let us just start solving some problems. So let us start with this relation. The material time derivative of the deformation gradient is nothing but the velocity gradient acting on the deformation gradient itself. So this is let's start. This is a very fundamental proof. This will be used repeatedly in the upcoming sections of the course. So what is the material time derivative? Material time derivative is of any quantity phi is nothing but d phi by dt, keeping the material point constant. So if you have a body and it is deforming to some other body, you look at a material point here and you keep tracking where that material point is going. Say that material point goes here, just small x. Now you're looking at the variation. Say this could be the temperature field. So you have some field defined here. So you're looking at the same point, capital X, and you're seeing how the variation, how the temperature at that material point is varying with time. So that is the material time derivative. So this is the material time derivative. This is the material time derivative. This is the definition of material time derivative. So you fix the material point and then you keep looking at it. Suppose you're throwing a ball, right? You're throwing a ball somewhere else, and say you have a tunnel. Let's just make some innovative examples. You have a tunnel. and there's a kid. Say this tunnel has a fire here, and say you're throwing a ball through the tunnel to the other side on the ground. Right? So here the temperature is say 20 degrees Celsius. Somewhere inside, say it is some 45 degrees Celsius, and outside the tunnel it's again 20 degrees Celsius. Now you can plot the temperature as a function of the x coordinate of the ball itself. So that is one. So in a spatial setting, in an Eulerian setting, if you plot the temperature distribution, this is small x, right? This is the small x, this is the spatial x, this is x. So let's say where the ball is released, that is x equal to 0. So until this point, the temperature is at 20 degrees. And somewhere in between, the temperature goes up to 45 degrees. And as you reach the end of the tunnel, the temperature is again 20 degrees. So this is 20 degrees. So say this is temperature, and this is 20 degrees. And this is 45 degrees. And beyond the tunnel, it is just constant. Say, right? Okay. So this is the Eulerian description. You look at the space, you take a snapshot of, and this can be at any time, say t greater than 0. So you look at the entire scene, you take a snapshot of the scene at any instant, you get some, and you look at how the field is varying. So the temperature, how the temperature field is varying with x and y. So this is the Eulerian description. On the other hand, say Lagrangian, if you look at a Lagrangian setting, you have to fix a point where you're looking at the time evolution of temperature. So say you're fixing your coordinate, you're fixing your focus to the ball, fixing the focus to the ball, and the ball's position varies with time. So that doesn't matter. So you have to look at the temperature field as how it is varying with time. So as long as the ball is traveling, uh, so the horizontal velocity, if it's in projectile motion, you know that the horizontal velocity is constant. So there is a direct, it's proportional to time. So until the ball, say at 2 seconds, it reaches here. Say at 2 seconds, the ball reaches this end, and at 6 seconds, the ball reaches the other end. So until 2 seconds, the temperature of the ball will be 20. So 20 degrees Celsius, which is room temperature. So until 2 seconds, the ball's temperature will remain at 20. And somewhere in between, the ball's temperature reaches 45, and it comes down to uh, 20 degrees at the end of when the ball goes to the end of the tunnel at 6 seconds, and then it'll continue at 20 seconds. 20 degrees Celsius. So here note the coordinates. Here it is time versus the temperature of the ball. Here it is space versus the temperature at that x. And this is at a given t is equal to t naught. This is at a given material point, capital X. So this is the Lagrangian description, and this is the Eulerian description. So in the Lagrangian description, you look at the time derivative. So the slope of this curve is nothing but the material time derivative. If you take the slope of this curve, what it is the spatial gradient, or simply gradient. So you look at this. So here when you take the slope of the evolution of some field with respect to time at a fixed material point, that is the material time derivative. And if you take a snapshot in a given time, and then you look at how field is varying at that instant at this point, that is the spatial gradient. Now, okay, so this much is enough. This much is actually enough. So basically, material time derivative is you track a material point and then look at how the fields are varying with respect to time. So first thing that we set out to prove is d by dt of some field is what, right? So every field can be written either as a function of the spatial coordinate x and time t, or it can be written as a function of the material coordinate and the time t. So whenever I refer to the material coordinate, I put a cap, a small cap on top. And whenever I refer to the spatial coordinate, I just write a italic Greek symbol. Now, let us look at it further. Now, suppose I pour water and turn off this fire at some other point, say at time t is equal to 3 times t naught. Suppose there's no fire. Then what will happen? This will eventually cool down and there'll be no temperature distribution. Say temperature distribution will be something smaller. So temperature distribution also varies with time. Now you just take a fixed point here. You take a fixed point in the space and you have a stream of particles passing through that point. The ball can pass, the air can pass, whatever particle is passing through that point, record the temperature of that particle as T. So that is the spatial description. So this is the Eulerian Lagrangian, right? So this can be, so this is nothing but the derivative of the field, the Lagrangian field quantity, keeping x fixed. Now, how do we do this? We can always write it as, so this can be written as, so d by dt of phi is nothing but the material time derivative of keeping the coordinate fixed, which is nothing but use the chain rule. You can write this as the partial derivative. So phi is a function, the Lagrangian, this is a function of x and t. I can write this as this at a fixed x, and how x varies with plus. So you see what I have done, right? So this, or let me do it. So this is nothing but phi of dou phi by dou t of, sorry, not dou phi by dou t. So phi cap of x comma t is nothing but phi cap of x of x comma t, and this is nothing but phi of x comma t, right? So what I'm saying is, at every point you fix a spatial point, large number of materials will pass through that point. Now at every instant you look at what particle is passing through that point and take its temperature. But the particle that is passing through a given material point, a spatial point, say I'm fixing the spatial point as 2 comma 4, and some air is flowing through that point. So the same particle will not be staying at 2 comma 4, right? A large at time t equal to 0, one particle will pass through 2 comma 4. At time t equal to 1 second, some other particle will pass through that. Now I'm recording the temperature of these particles. Now the particle itself, the particle capital X, which passes through a given spatial point small x, is itself a function of time. Therefore this capital X is also a function of small x and time. Now let us just substitute here, right? We just have d by dt of phi cap of x, x of x comma t comma t. This is at a capital, this fixed capital X. Now what is this? Here we can use the chain rule. So this is a function of something which itself is a function of t. So here first you put partial phi with respect to x and partial x with respect to small x. Is that all? No. Sorry, partial x with respect to time t. Okay. Plus you have right. So So what is this capital? What is the rate of change of position of a given particle with respect to time? That is the velocity dot so but what is this? What is this quantity? This is nothing but the variation of a field, which is a function of x and x. Just a minute, let me just check. Yeah. Let me just. So what I said is we can have a Lagrangian description or an Eulerian description, but this small x is itself a function of capital X and time. Now the material time derivative of a given field is nothing but d by dt of phi cap. Now phi cap, there are only two independent variables. So this while keeping x constant. So this I can put a partial sign, a partial phi cap with respect to time. But what is this? This is partial t of phi of x comma t keeping x fixed. Use the chain rule. So first you have phi with respect to x and x with respect to t keeping capital X fixed plus phi with respect to t keeping small x fixed. So note this is the spatial derivative with respect to velocity, spatial time derivative. This is the um, spatial gradient. So what is this? This is grad phi dot. What is the rate of change of position with respect to time keeping the material point fixed? It is the velocity. Plus here what do we have? Here it is the rate of change of the field at that fixed point. So this is how the material time derivative is defined. Now let us look at the material time derivative of the deformation gradient. That is where we started with material time derivative of deformation gradient. So f is a tensor and it's a function both of x and t, and you're looking at its material time derivative. Use that formula. It is nothing but the spatial derivative of f plus This is at a fixed x plus what? We have the velocity times or rather use the initial notation Fij of x comma t. You have an Fij here, and here the dot product will be just Vk dou Fij by dou xk. This is okay. Now, this is with the understanding this is constant. So now let us find out what is this, right? So this is nothing but dou by dou t of what is Fij? Dou xi by dou xj plus Vk dou by dou small xk of dou xi by dou xj. But what is dou xi by dou xj? The spatial gradient of itself is this is nothing but delta ij. So we have dou by dou t of dou xi by dou capital Xj plus Vk dou by dou xk of delta ij. But delta ij is a constant. It takes the value either 1 or 0 depending on whether xi is equal to j or I not equal to j. It doesn't have any x dependence, so this is 0. What is the first term? It's nothing but you can interchange the mixed derivatives. You get dou by uh, dou capital Xj of dou xi by dou t. But this is nothing but dou vi by dou capital Xj. Is this the velocity gradient? No, this is not the velocity gradient. Why? This is the material gradient. Well, this is the derivative of the velocity field with respect to the material coordinate x. It is not the gradient of the velocity field. So again, to do this, use the chain rule. It's just one step. Dou vi by dou capital Xj is nothing but dou vi by dou small xj multiplied with xk, dou small xk by dou capital Xj. So use the chain rule. Now we get it. So this, what is the first term? Dou vi by dou small xj is the velocity gradient L I k, and here we have small x by capital X, which is nothing but fkj. So d by dt of Fij is nothing but Lik Fkj. In tensorial notation, you can drop the indices Fij. You can write it as df by dt is nothing but Lf. Now let us prove some result. So let us prove this result. Look at this. So this is a transport theorem. D by dt of you have a closed loop C. Let me just have it as C. Phi is a scalar field. Dx, okay, is equal to integral over C d phi by dt plus phi L dx. So follow carefully. This is an important result. So now what does the left hand side mean, right? So let us look at it very carefully. You have a body. You have a body like this at any time t greater than 0. You're taking a snapshot of a body. In that body, you are considering a loop C. It is just a closed loop C. Okay, this is a closed loop C. At any time you're taking a snapshot, you're taking a closed loop C. Phi is some scalar field. This is some scalar. Scalar field means it is defined everywhere in space. Phi of x, y, z, t. It's defined everywhere. and you're integrating this scalar field over this curve. So you're considering a small infinitesimal length d small x here, right? You're considering a small infinitesimal length d small x along this curve. You look at the value of the scalar field at this point, multiply by dx, and keep adding up. So basically integrating along this curve. So what will be the resultant? Resultant will be a vector, right? This is a scalar field. You're scaling an infinitesimal element by the scalar field value and add them all up through the curve. And you take its time derivative. So this curve itself is fixed in time, but the body may move in time. So the body can go to some other point like this. Let's say this is the body at time t greater than, say this is a t naught greater than, this is a t1 greater than t naught. At some other point, the body can go somewhere else, but the curve is still at the same spatial coordinate, spatial location. So this will be what? So how do we find this? We are integrating it and you're finding the derivative of the integrated quantity. So here, this is a transport theorem. This is a transport theorem. Now let us solve this. Okay. So the left hand side is, let's solve in a fresh page. The left hand side is d by dt of, you put a curve phi dx. The curve, the description of the curve itself is not independent of the material coordinate, because as the body is deforming, different material points are lying along the curve. Therefore, you cannot take the derivative directly into the integral. So what do? We have to transform everything that is inside the integral to the spatial material coordinates. So this is a Lagrange, this is an Eulerian description. This is an Eulerian description. Let us get back to the Lagrangian description. So what am I doing? What I'm doing is look at this curve and look at the pre-image of this curve in a Lagrangian. Say this curve at time t naught greater than 0 would have come from some other curve. The some other curve could have been something like this, say c naught. So this is at time t equal to 0. So the points that are now lying along the curve c have come from the curve c naught in the material coordinates, in the material body. Initially there is a curve c naught. There are some points on this curve. As the solid deforms, this curve deforms into c. And this time derivative depends on the material point. Therefore, you cannot take the time derivative inside without changing the integral to Lagrangian description. So let me write it in Lagrangian description as integrated over C naught. The points are not going to change. So instead of phi, it will be phi cap, which is described as a function of x and t. And what else? What is dx? So you have a dx of x and t, right? And this is d by dt. And this is an Lagrangian description. So what is dx of x comma t? Simple. This is nothing but f dx, right? This is the basic result. So the right hand side is equal to, so left hand side is equal to d by dt of integral c naught phi cap f dx. Now on the right hand side, everything is a function only of the material coordinate capital X and the time. So this can be directly brought in because C0 does not depend on time. So this can be written as integral C naught, the material time derivative of phi cap f dx. Dx does not depend on time, it's a material vector. So this derivative acts only on the first two. So you get integral C naught d phi cap dt f plus phi cap df by dt dx. So this is a tensor, this is a tensor, this is a scalar, this is a scalar, this is a vector. So resultant has to be a vector. Simplify this further. What is So this is a Lagrangian description. The rate of change of a quantity or at a material point with time is nothing but the material time derivative of the field in Euclidean description. So this does not change. And what about, and this in fact this is equal to what? Dou phi by dou t at a fixed spatial point plus the gradient of the field, spatial gradient of the field dot product with the velocity at that spatial point, velocity of x comma t. And what about the second term? Second term has a df by dt. We just proved that df by dt is nothing but LF. Right? Now we'll substitute these back into this right hand side expression. We get left hand side is equal to integral C naught d phi by dt plus phi phi cap. This is still cap LF and here you have an F, right? Here you have an F. D phi F. Split the two terms, you get integral C naught d phi cap dt f dx plus C naught phi cap L f dx. So look at f dx. What is f dx? It is nothing but d small x. And so once you go from Eulerian to Lagrangian, so sorry, Lagrangian to Eulerian. Again, since you are going to Eulerian, let me change the color to red. So this will be, so you are integrating now f dx is a spatial infinitesimal vector. So the limit of the integral goes from C naught to C. So I'm going from Lagrangian to Eulerian. So this becomes d phi. So cap will go away as you go to Eulerian. Dx plus integral C. You get a phi. Cap will go away. L dx. So put them together. You get d by dt of C phi dx is nothing but integral over the same curve d phi by dt plus phi L dx. So this we approve the first transport law. Okay. Yeah, I hope this is okay. Then let us look at some other another simple law, simple theorem. So this is another transport theorem. So this is the second one, d by dt of integral C phi ds. So here ds is, it's a scalar, this is a scalar, so net result has to be a scalar. This is equal to, prove that this is equal to C d phi by dt plus phi lambda dot d lambda ds, where lambda is the unit vector along the curve. So you have a curve here. At any point, the curve has a direction, and in that direction you draw a tangent, unit vector tangential to the curve. So lambda is a unit tangent to the curve. I'm sorry. So what do we do? So let's solve this problem. Start with the left hand side as usual. So we are still in the Lagrangian Eulerian coordinates, Eulerian description, d by dt of phi ds. This is the curve C. As we did in the last time, take it back to the Lagrangian. So what should I do? I'll change the color to green. So this will be d by dt of C naught. So ds is an infinitesimal segment in the deformed coordinates. I have to go back to Eulerian, what should I have here? ds naught. The integral it should be over ds naught. But how is ds and ds naught related? We'll come to it. So phi will become just phi cap, and here there should be something ds naught. Let us see what it is. So we have that ds square is equal to dx dot dx, but this is nothing but f dx dot f dx. This is nothing but dx dot f transpose f dx, and this is nothing but dx dot c dx. So this do you have d small s, right? So we have a d small s. So what about d small s? It is nothing but square root of dx dot c dx. But let us say dx is equal to ds naught lambda naught, where lambda naught is the unit tangent to the curve c naught. So this is a different c, that's a different c, right? So let me put a double c here. This is the this is the Cauchy green tensor, right? Cauchy green tensor. So here it's lambda naught dx, right? So you have ds naught. So this will become square root of, you get a ds naught here, lambda naught dot c lambda naught, you have another ds naught, so this becomes a ds naught square. So this you can write it as ds naught times square root of lambda naught dot c lambda naught. Sorry, c is not a vector. Okay. Now so let's so the left hand side is nothing but d by dt of integral over the initial curve phi cap, you get a square root of lambda naught c dot c lambda naught ds naught. Now everything is independent of time, so you can take the derivative inside. So you get integral c naught d by dt of phi lambda naught dot c lambda naught ds naught. I use the product rule. We get c naught d phi by dt. The rest stays as it is, square root of lambda naught dot c lambda naught ds naught. Plus the second term is phi stays as it is, and the derivative acts on the second term is d by dt of square root of lambda naught dot c lambda naught ds naught. So do this transformation back, right? Reverse these steps. So this is basically ds, right? So let's just have it how it is. So let us call this term 1 and let's call this term 2. Now I'm doing everything in the Lagrangian coordinate. So what is the term 2? It is nothing but integral c naught phi, this is a scalar, d by dt of square root of lambda naught dot c lambda naught ds naught. I can take this ds naught into the square root. So what I get is ds integral ds. So what I'm getting is integral c naught phi ds by dt. Okay, so the next step is to find this quantity. Right? We have to find out what this quantity is. This is not required. So let's just do this. So here we have a d by dt of the square root term. ds naught does not depend on time. So you have d by dt of square root of lambda naught dot c lambda naught. And what it is? So square root of a certain function is 1 by 2 square root of lambda naught dot c lambda naught. And in the new, so this is a scalar. This with what is there inside the thing, differentiate that. Lambda naught is independent of time. So we have dot d acting on lambda naught. What is dc by dt? So dc by dt, you can use the chain rule. dc by dt is nothing but dou c by dou f dot dou f by dou t. Okay, so dc by dt. Okay, so let's do one thing. We don't need this. So dc by dt, let's find out directly. It is d by dt of f transpose f. So this is nothing but df by dt transpose f plus df by dt f transpose df by dt. And what is df by dt? It is lf, right? lf transpose f plus f transpose lf. So use the transpose law, you get f transpose L transpose f plus f transpose LF. Club the two, you get f transpose L transpose plus L f, which is f transpose 2d f. So d is the symmetric part of the velocity gradient L. L transpose plus L is 2 times the symmetric part. So this is nothing but 2 times f transpose L d f. Plug this into this one. So dc by dt is, so we have 1 by 2 square root of lambda naught dot c lambda naught. This will be lambda naught dot 2 times f transpose d f lambda naught. And what do we have here? This there's a ds naught here. So the term 2 is equal to, so this 2 and 2 gets cancelled. This 2 and this 2 gets cancelled. So you get a lambda naught dot f transpose df f transpose d f. This is a tensor that acts on lambda naught. Okay. Divided by lambda naught, root of lambda naught c lambda naught. So divided by square root of lambda naught dot c lambda naught. We're getting close to the solution. So, okay. And you have a ds outside, right? You have a ds naught and this one here. So you have integral over c naught, this entire thing multiplied by phi cap, and you have a ds naught. Now let us multiply and divide by this quantity. Okay. So let us multiply and divide by this quantity, square root of lambda naught dot c lambda naught. So you get lambda naught, and this f transpose can be brought to the other side. So you get f lambda naught dot df lambda naught divided by lambda naught dot c lambda naught. You get a phi cap. You get square root of lambda naught dot c lambda naught ds naught. What is this? This is nothing but ds. So in Eulerian, this term together is nothing but ds. F lambda naught is what? F lambda naught is, so F lambda naught is, you can write this as, so lambda naught is a unit tangent vector. So this is F dx by ds naught, right? So this is F dx by dx naught. And this you can further write this as dx by ds naught. This is dx by ds naught, and this one is also F lambda naught is dx by ds naught. But what do we have in the denominator? We'll get a, so this ds naught goes here. So you get this as integral over c dx dot d dx phi cap divided by ds naught lambda dot c ds naught lambda dot, and this will end, this entire thing will become ds. So what do we have in the denominator? It is ds naught lambda naught c is this thing. So this is basically c dx dot d dx d small s divided by, this is nothing but d capital X dot c d capital X, and so denominator we have a ds square. So write it further. We have this is equal to integral dx is what? Ds lambda dot d ds lambda ds divided by dx is in denominator we have a ds dx c dot dx, which is nothing but ds square. It's a ds square. So this goes away, and you're left with integral over the current c in the Eulerian description. It is current c lambda dot d lambda ds, and denominator is just 1. So this is the second term. What is the first term? So first term, again, this is nothing but ds. So club the two together, we get d by dt of, or any spatial curve c, phi ds is nothing but integral over the same spatial curve, material time derivative of the field, plus lambda dot d lambda, entire thing ds. So this is the other transport theorem for curves. So these will not, you can derive it whenever you want, nothing to remember here, but this is just to make sure the ideas of Lagrangian and Eulerian descriptions are clear. Next, let us solve, I hope this is clear. You can ask me if there's any doubt. You can ask me if there's any doubt. Next, let us solve a stress transformation or stress problem. So the stress components at the origin are given by, let me state the problem here. The stress components at the origin on the surface x square plus y square plus z square plus 2x plus 4y plus 4z is equal to 0. R 2 minus 1 0 minus 1 2 0 0 0 4. Okay, so let me do one thing. There is a slight issue here. So the stress components at the origin of something. Okay, this is just something. There is some body, and there is an origin inside that body. And at the origin, the stress component is given by this. Now, first question is, so this is the third question. Find the normal stress on the surface at the origin. So this is the surface of a sphere probably. This is probably the surface of a sphere. And as you can see, this sphere passes through the origin. So this sphere could be, I'll show it in a different color. So this is the surface of this surface is some surface like this. It passes through the origin. Now, as I explained a few classes ago, the stress is defined at a point. You don't need a surface to define the stress. Traction is defined on a surface at a given point. Now find the normal stress on the surface at the origin. So let's look at the first problem. Okay. So you have a surface and this is a point on the surface. At that point, I know the stress tensor and I want the normal, and on this surface, I can have both normal and uh, tangential shear, tangential tractions. I'm interested in the normal traction. Okay. So this is the normal. Let us call it sigma n. And this is the traction vector t. And you have a stress t. So how is t related to sigma? This you should know by now. T is equal to the stress tensor acting on the normal end. Okay. And what is the normal component of traction? So this surface has a normal here. So the surface has got a small normal, unit normal here, which is n. And you have a vector. The component of a vector along a given unit vector is nothing but, this can be any vector b. The component of a vector along a given unit vector is nothing but v dot n. Why? It is just v n cos theta. This is just 1. So it is just v cos theta. Cos is the angle between the two. This you know. So sigma n is nothing but t dot n. So therefore, the normal component of stress on a given surface at a given point is nothing but sigma n, which is n dot t, which in turn is n dot sigma n. What is n? What is n? So we need to find a normal. We need to find an outward normal to the surface. Let us do that. So how to find a normal? So in the calculus, multivariable calculus that in first year BTech you could have studied. So if there's a surface defined as f of x comma y comma z equal to 0, this defines a three-dimensional surface. F of x comma y comma z equal to 0 is the implicit equation of a three-dimensional surface. Now the equation of if you take the gradient of this, if you take the grad f, right? If you take gradient of f, that is a vector. The gradient of a grad f is the vector field normal to this surface at every point. Okay, so You have a three-dimensional surface defined as f of, so implicit equation of a three-dimensional surface. We have a 3D surface defined as f of x, y, z equal to 0. The normal field, the vector field grad f is normal to f of x, y, z equal to 0. Why? We can see that later. Why is grad f normal to this? We'll see that later, right? The reason for that is if you make some small changes. So the gradient is defined as uh, grad f dot dx is the directional derivative at a given point. So if this quantity itself is 0, as you move along a surface, it means this remains 0. As long as you move along points x, y, z, which obeys this, it is 0. Then the normal, so if you go from f of x, y, z to f of x plus dx, y plus dy, z plus dz, and you ensure that x, y, z still remain on the same surface, the difference between the two is nothing but grad f dot dx, dy, dz. Dx, dy, dz are arbitrary scalars. This has to be equal to 0 as long as you remain on the surface, which means grad f has to be normal to any perturbation in the surface, which means this is normal. It is perpendicular to dx. This is dx, dy, dz. So this is a basic result you might have seen in physics or maths. So the normal vector field to a given surface f of x, y, z equal to 0 is given by grad f. So we can use that to find the outward normal to the sphere. So here our f of x comma y comma z is what? It is x square plus y square plus z square plus 2x plus 4y plus 4z. What is grad f? It is nothing but 2x. This is independent of x plus 2 ex plus 2y plus 4 ey plus 2z plus 4 ez. So this is the normal to this surface. Now, which is the point of interest? The stress is given at the origin. So the gradient at the origin has components 2, 4, 4. But this is the gradient. We want to get a normal, so normalize it. So it is 2, 4, 4 divided by the length of the vector, which is square root of 2 square plus 4 square plus 4 square. So 4 square 16, 16 plus 16 32, 32 plus 4 is 40. So you get 2, 4, 4 by square root of 40. Now we are already given the stress at that point. So let us find the traction at this point. So the traction is sigma n. Sigma is 2 minus 1 0 minus 1 2 0 0 0 4. What is the normal? Normal is 1 by square root of 40, which is a scalar. This is not acting on this is acting on the normal 2 4 4. So this you can write as root 40, you can write as 1 by 2 root 10. And then multiply this 2 2s are 4, 4 minus 4 0, and minus 2 plus 8, which is 6. And the last one is 0 0 16. So this is basically the traction on this surface is 0, 3 by square root of 10 and 8 by square root of 10. What is the next step? We want sigma n, which is n dot t. So this is another 1 by root 40, 2 4 4. So dot product I can write it as row vector multiplied by a column vector. 0, 3 by square root of 10, 8 by square root of 10. And this is nothing but 1 by root 40, 1 by 2 root 10 of 2 zeros are 0 plus 4, 3, 12, 12 by root 10 plus 4, 8, 32, 32 by root 10. So here this will become 6 plus 16 by 10. So 16, 6, root 10, root 10, 10. 6 plus 16 is 22. So it is nothing but 2.2. So the normal stress component is nothing but 2.2. Okay. Next, find the principal stresses and the equation of the plane through the origin for which the normal stress is a maximum. We'll do that. So next, the second part of the question is find the principal stresses. And principal directions. So what is the principal stress plane? So there exists a given plane on which the traction is just proportional to the normal, right? So the traction is just normal. There are no shear stresses. So traction is equal to some lambda n. There exists a plane on which the traction is only normal. There are no shear stresses. That is how you define a principal plane. And on this plane, the traction is just normal to the plane, which means the traction is just proportional to the normal. But what is traction itself? It is sigma n. This is equal to lambda n. So we need to solve the eigenvalue problem, sigma n equal to lambda n, in order to find the principal stresses and principal directions. So let us do that. Let us take n as n1, n2, n3. And sigma is what? Sigma is 2 minus 1, 0, minus 1, 2, 0, 0, 0, 4. So let us solve this problem. To solve this, the condition is, so this one trivial solution is n equal to 0. To get non-trivial solutions, you have to set determinant of sigma minus lambda I equal to 0. Let's do that. So sigma minus lambda is what? It is 2 minus lambda minus 1, 0, minus 1, 2 minus lambda, 0, 0, 0, 4 minus lambda. Yeah, so this system should have trivial solutions, which means the determinant of this has to be 0. So what is the determinant of this matrix? It is 4 minus lambda, 2 minus lambda the whole square, minus 1. Should be equal to 0. So one root is 4 minus lambda, the other root is 2 minus 2 lambda plus lambda square minus 1 is equal to 0. So we have 4 minus lambda, lambda square minus 2 lambda plus 1 equal to 0. So we get 4 minus lambda, lambda minus 1, lambda minus 1. So the roots of this equation are lambda equal to 1, lambda equal to 1, lambda equal to 4. So the maximum principal stress, the maximum principal stress sigma 1 is equal to 4. Other two principal stresses are 1. So corresponding to sigma, we are asked to find out which plane the maximum principal stress is achieved. So what is that plane? That plane is normal to n1, n2, n3. We have to find the equation of the plane. Let's do it. So now solve the system. Sigma is equal to n. So we want to solve sigma n is equal to sigma 1 n. This is the plane along which the maximum principal stress is achieved. So it is, and you just do it, you get sigma minus sigma 1 n is equal to 0. This you will get the n. So this is okay. Yeah. So the first eigenvalue is 4. You get 2 minus 4, minus 1, 0, minus 1, 2 minus 4, 0, 0, 0, 4 minus 4. And the normal to this is n1, n2, n3. This is equal to 0, 0, 0. So what is the system? Minus 2, minus 1, 0, minus 1, minus 2, 0, 0, 0, 0, n1, n2, n3, 0, 0, 0. The last equation is trivial. From the first two equations, we get n1 equal to 0, n2 equal to 0, right? You solve this. One equation is minus 2 n1 minus 1 n2 is equal to 0. And the other equation is minus n1 minus 2 n2 equal to 0. These two coefficients are not proportional to each other. Therefore, the only solution is the trivial solution is n1 equal to n2 equal to 0. And n3 can be arbitrary. Let us choose it as 1 so that it's a unit vector. So one plane on which the stresses are maximum is n3 equal to 1, which is the xy plane. So one vector, the principal vector along which the maximum principal stresses are lying is 0, 0, 1, which is the normal to xy plane. What is the equation of this plane? It is z equal to 0, right? So if the normal has components n1, n2, n3, the plane has equation n1x plus n2y plus n3z plus d equal to 0, where d is the constant that defines through which point the plane is passing. So in this case, the plane is passing through the origin, so d equal to 0 as origin, and n1, n2, n3 are the components of the normal. So the plane equation is z equal to 0. What are the other principal directions? The other principal, so xy plane itself, all xy plane is a principal plane, and the other two principal axis we need to find out. So for that, sigma 2, sigma 3, 1 we should take. So 2 minus 1, minus 1, 0, minus 1, 2 minus 1, 0, 0, 0, 4, 4 minus 1. n1, n2, n3. These are the other principal planes. This is equal to 0, 0, 0. So if you solve, we'll get first one is 1 minus 1, 0, minus 1, 1, 0, 0, 0, t. n1, n2, n3 equal to 0, 0, 0. So one solution is n3 equal to 0. This has to be satisfied. And what is the other? n1 equal to 2. Okay. So the other plane, one possibility, other plane is you can have 1 by root 2, 1 by root 2, 0. Let's see. Where did we solve the characters? Yeah, 2 minus. This is a 4. Sorry, this is a mistake. This is a 4. This becomes a 3. Yeah, that's what I thought. So this is a mistake. I'm sorry for this. So this is a 4. This is a 3. So it is this is a 4. So the other two is 2. 2 and 1. Yeah, so lambda is equal to 2, lambda equal to 1. These are two other eigenvectors. I'm sorry for the mistake. So this is, so the other principal vector is, principal plane is x plus y equal to 0 is the other principal plane. Why? Because you can put 1 by root 2 x plus 1 by root 2 y plus 0z is equal to 0, which means x plus y is equal to 0. And the third eigenvalue is n equal to, so this is the minimum principal stress, and the third one is sigma 2. So here sigma 2 is not, yeah, so here I made a mistake. So this 1, 2, 4, these are the eigenvalues, and sigma 2 is equal to 2, sigma 3 is equal to 1 in the decreasing order of decreasing magnitude, right? So what is sigma 2? So corresponding to sigma 3, we found what the principal plane is. So for sigma 2 is equal to 2. So we need to solve 2 minus 2 minus 1, 0, minus 1, 2 minus 2, 0, 0, 0, 4 minus 2. This n1, n2, n3 is equal to 0, 0, 0. So the solution is 0 minus 1, 0, minus 1, 0, 0, 0, 0, 2. Sorry, again there is something off. This is 4 minus 4 lambda plus lambda square minus 1. 4 minus 1 is 3. So 3 is minus 3. Yeah, it is minus 4 lambda. So minus 4 we can get as minus 3 minus 1. So this, sorry, it's minus 3. So this is 3. So this is 3. Get a 3, 3. This is minus 1. This is minus 1. n1, n2, n3 equal to 0, 0, 0. So the other principal direction is n1 equal to minus n2, n3 equal to 0. So I get 0, minus 1, 1. 1 by root 2 if you want to normalize it. So the other principal plane is what? It is x minus y is equal to 0. So to summarize the answers for this question, at the point, at the origin, the normal stress is 2.2. The maximum principal stress is 4, which happens on the plane x, which happens on the plane z equal to 0. And the minimum principal stress is 1, which happens on the plane x plus y equal to 0. And there's also another principal plane, which is corresponding to a sigma of 3, which is x minus y is equal to 0. So yeah, we are almost time. It's almost time. Let us end the session here. If you have any questions, you can ask me. I'll wait for a few minutes. You can
Hello,
ask.
Naresh.
Yes.
Just now I joined, man. I was just now I reached my flat, so I'm not able to watch your session. But I saw that you were solving the question what I was sent to you. So thank you so much. I will go through the video.
Okay. Okay. Yes. Yes.
Yeah, yeah.
Sorry. Hello. I'm not able to hear. Hello.
I'm
Somehow.
audible.
Yeah. Now
Hello.
you're audible. Yes. Yes.
Okay. Okay. So that's why I'm telling that I will go through your video, and if any doubt is there, then I will contact you.
Okay. Okay. Yes. Yes. I think I have explained that
Yeah.
issue. There's no problem. We also have some more
Okay.
questions. Yeah. Yeah. I'll upload it and then you can look at them.
Yeah. Yes. Yes.
Yeah. Anyway, thanks. Thanks for attending. So I can end the
Yeah.
session, right?
Thank you.
Yeah. Okay. Let me stop recording. Thanks for attending.
Yeah. Thank you.